this new chapter is dedicated to the whole new idea of vector fields. Well, suppose you have a fan and this fan starts working. So as you can see, the movement of the fan creates some vectors. These vectors starts rotating, and we can use functions that we call vector functions to define the behavior of the vectors here. Then, as you can see, you do not have just one vector. You have a collection of vectors that are rotating. Well, this set of vectors is called a vector field. Next example. Think about the hurricane, for example, Katrina or any other hurricane that you heard about. As you can see, when it comes to hurricane, you have a field of vectors that are start rotating, or they might have other behavior. It's not always about rotation. Sometimes you have some linear relation that shows the behavior of those vectors. So the set of these vectors, the collection of these vectors that follow the behavior, in this case, a rotational behavior, is called a vector field. We can use a vector valued function to define the set of vectors. Another example. Well, think about the Earth, the magnetic field of the Earth, North Pole and South Pole. Well, the vector fields that is created here by magnetic vectors that are coming from the south and going into the North Pole forms a vector field that we call magnetic field. Again, we can define a function, a vector function that describes this behavior. So as you can see here, you have a collection, a set of vectors that form a vector field. And finally, this is a real life example, real picture of magnetic field, and look at the behavior. In each position, at each X and Y value, you have vectors in different directions. Again, we can define a function, a vector valued function, to describe the behavior of these vectors that form something that we call a vector field, a field full with vectors. Awesome. So our objective today is talking about vector field. How do we define a vector field? Well, definition. In this definition, we're going to define a vector field this way. We can define a vector field in two-dimensional space, and you can define a vector field in three-dimensional space. So suppose we have a domain. Let V be a subset of the plane. Remember, how do we define the plane? Plane is R Cartesian product with R, or R to the second power. A vector field, a two-dimensional vector field. So the name vector field is a function. What function? The function is defined this way. F of x comma y, which is in the form of a vector. It's equal to, so remember that when you're talking about vectors, we use a specific symbol, the vector symbol. The very first component of this function as a vector is a real value function. So I'm going to write this guy down with a different color, f of x comma y. And the second component of this vector is another real valued function, g of x and y. So suppose D be a subset of the plane, a two-dimensional vector field is nothing but a function that is defined in the form of a vector. The first component of the vector is a function, and the second component of this vector is also another function. So this is our first component. And this is our second component. So remember that back in elementary calculus, we talked about vectors. Recall? In elementary calculus, we introduced vectors. You said that, well, a vector like V is defined as the symbol for a vector has first component A, second component B. Or, for example, if you think about the standard vectors, this is vector 1 and 0. The vector that represents x-axis. We can define another vector, u, which is equal to 0 and 1, which is the vector representing the y-axis, and so on. In this case, in multivariable calculus, we say that, hey, instead of just defining numbers for first component, second component, we're going to use functions like f of x and y and g of x and y. It means that as the position, x and y represent the position, as the position is changing, the vector is changing as well. So note that. Note. As x and y are changing, x comma y are changing, it means that the position is changing. Well, the position of the function is changing, so the vectors are changing as well. The position is changing, so as our vectors. This guy represents a lot of vectors in the plane. So it might be like this. In xy plane, you might have x-axis and y-axis. You might see this function, representation of this function as collections of vectors. What vectors? Any vectors. The vector might be behaving this way, or they might behave differently based on the definition of your function. It might be a rotational vector field, or it might be absolutely different from this behavior. So when you see a set of vectors, this set of vectors has a function, a vector field, which is a function with this representation. It's not like, you know, the examples that we saw before. It's not like exactly a surface, a nice surface, or a line, or parabola, or circle. It has some vectors representing the graph of this function or the behavior of this function. Another note for you. Another note for you. Fx, y, and gxy, both of them are real valued functions. What's the meaning of that? F of x and y and g of x and y are real valued functions. It means that their output values are real numbers. Their output values are real numbers. It means that it can be fraction, it can be radical, fraction, 1/5, I don't know, 2/3, plus minus square root of 2, and the rest of these values, pi, it might be anything. But your vector field is a vector valued function. So another note, remember these terminologies, these are important. So real valued function and vector valued function. So last note here. So the highlighted F, capital F, X and Y, is a vector valued function. What's the meaning of that? It means that the output of this function is not exactly a real number. It is a vector. It means that the outputs of f of the bolded f of x and y are vectors. Like what? Like 1, 0, like a half, negative, a third, and so on. These are the output values of vector function, which in this case, you have a vector field. Very well. Give us an example. One example for you and how to graph a vector field in the plane. Later on, we're going to introduce a vector field in the space and learn how to graph it in the space. Remember that it's just a collection of vectors. Example. Graph vector field. So this vector field is defined by this function. The function is f of the bolded f representing your vector field, vector valued function, which is, well, the first component is negative y, and the second component is x. Very well. Okay. First of all, let's just write down a small review here. Recall that any vector, it doesn't matter if it's a vector field or it's just a vector, any vector like v, which is defined as a comma b, can be written as v equals to a times I plus b times j. Remember that I was the unit vector representing x-axis and j was the unit vector representing y-axis. So based on the definition that we saw before, we can rewrite this function, this vector function, using I and j as well. So let me write that note for you. We can also represent f of x and y as negative y times I plus x times j. So when you write the vector function, vector field this way, it means that the first component is negative y and the second component is just x. So question says, graph this vector function, graph this vector field. How do we graph this? Very well. So remember that I said as x and y are changing, the position are changing, it means that your vectors are changing. So what's the meaning of that? How do we graph any function? We plug in different values for our x and y. To graph any function, from algebra, we plug in different values into the function. So remember that if you have function f of x equals to, I don't know, x, you use a table, you say that, hey, I have x and I have some y values, which is equal to x. I plug in, for example, 0 for x, then f of x or the y value is 0. Then I plug in 1 for x, my y value is 1. I plug in 2 for x, my y value is 2, and so on, negative 2, negative 2. Point plotting. We're going to do the same thing when it comes to vector fields. The exact same process. To graph our function, this is just a function. X and y are changing. Use a table. We use a table. So I'll show you how to use a table to graph this by hand, but later on, we're going to use technology to graph any vector field for us. It takes forever to graph a vector field. So we're going to just practice, see how we graph a vector field, but later on, when it comes to your homework questions, your quizzes, your exams, I expect you to use technology. So remember that your x and y are changing. It means that you have to plug in different values for x and y. So x, comma, y. Then the value for your function, the output value is a vector. Output is negative y, comma, x. So let's plug in different values for our x, for our y. So the very first one that I want to plug in is 1 and 0. If my x is 1, let me use a different color for x and y. So for y, I'm going to use red, and for x, I'm going to use purple. So suppose x is 1, and your y is, for example, 0. Easy numbers, simple numbers. So this is my very first point. This is my input values, inputs, and now I have to calculate the output value. The output is equal to, well, the first component is minus y. Well, minus y. What is my y value? My y value is 0. So it means that my first component is just 0. Why is that? Because my y is 0. What about the second component? The second component is x. What is my x? X is 1. So let's just write this down, which is a vector. It means that I have to graph a vector here. Well, okay. Let's see. This is my x-axis. This is my y-axis. And then I have 0 and 1. This is the vector that I'm going to graph. 0 and 1. Zero and 1. So now I expect you to ask, what about the input values? How do I use the input values? I found this vector. Well, shouldn't this be starting at this point, related to the position? So what do you think? Remember that you're using a position. What is the position of this vector? Well, the position of this vector is 1 and 0. So we have to take the position into account as well. So this is our position. At this position, at position 1 and 0, this is the position 1 and 0, you have a vector which is 0 and 1. Well, let's plug in another set of x and y values. So let us plug in, for example, let's see, 2 and 2. Let us plug in 2 for x and 2 for y. See, what do we have? 2 for x and 2 for y. Okay. My x is 2 and my y is 2 as well. So the output value at that position, that the particle is at this position, it assigns a vector as the output. Here you have, well, y is 2, so we get minus 2. And comma, x is also 2. Negative 2 and 2 at this position. So you have 2 and 2, and the position is negative 2 and 2. So where is 2 and 2? Where is the position? You have to identify the position first. 2 and, for example, this is 1 and 2. This is the position that you have. So how do we graph this vector? Negative 2 and 2. Remember that the magnitude of this vector is equal to square root of 4 plus 4, which is 8, or 2 square root of 2. So it's not exactly a unit vector. The length of this vector is larger than the length of the second vector. So this is another vector. And recall the norm. The magnitude of a vector if you have vector v, the magnitude of vector v is equal to square root of a squared plus b squared. So in this case, if you want to calculate the magnitude of this vector, it is 1, and the magnitude of the second vector is the square root of 8, or 2 square root of 2. So if you want to think about this vector, the behavior, first of all, the length is going to be larger than the first vector that you graph, and this vector has the direction -2 and 2. So at 2 and 2, this is the output value of your function. We can continue this process. If you have time, plug in more values. More values. Then it gives you a general idea of the behavior of this graph. Well, again, we are not really interested in using table, paper, and pencil to graph a vector field. We are interested in using technology to graph it. Let's take a look at 2 websites that help us to graph vector fields in 2D, 2-dimension. So in 2D, remember that the very first component that we had for our x, it was negative y and x. So we have negative y and positive x. And then, well, we can assign different values to x and y. Then it gives us a range of vectors in 2D space. This is the behavior of this vector field. It seems like we have a rotational vector field. It starts rotating like a fan. Remember the graph of a fan, or some part of the hurricane. Very well. So let's take a look at our vector field. Like this case. So if you have a fan and you start the fan, it starts rotating. Am I right? The panels are rotating, and the direction is rotational. It starts rotating very fast. Then you have some vectors. You create a vector field, a collection of vectors. So in our example here, we start using a function, and then this vector field, vector function, f of x and y, is defined as negative y and x. And as you saw, the graph is a rotational graph. So remember that you can use the website Academo, and it graphs the whole thing for you as well. Our first component is negative y, and the second component is x. So in xy plane, you can see the behavior of this rotational vector field. Very well. So as we define a vector field in 2D, we can define a vector field in 3D in the space itself. Very well. Note that we can define a vector field or vector function in the space. So when you define a vector field or vector function in the space, it means that it needs to have three components. Well, so suppose we define our vector field in the space this way. F of x, comma y, comma z. Now you have a position in the space. The position x, y, and z is equal to, well, here you can define using real valued function like p, q, and r. P of x, y, z, q of x, y, z, and r of x, y, z. So q of x, y, z, and r of x, y, z. Again, these components are all real valued functions. It means that if I plug in numbers for x, y, and z, the first component is a number, the second component is another number, and r, the last component, is also a number. So this is our first component. Which is a number. Second component. Which is another number. And the third component, which is another number. All of these are numbers, and then the output of this function is a vector. So this is going to be a vector. Again, you can represent this guy using I, J, and K. F of x, y, and z as a vector field, as a vector function, can be defined as, well, p of I, q of j, px, y, z times I representing x-axis plus q of x, y, z, j representing y-axis, and r of x, y, z, which represents, multiplied by k, represent the z-axis. So I is equal to 1, 0, 0, unit vector representing x-axis, j is unit vector representing y-axis, and k unit vector representing z-axis. Well, if we graph this vector field in this space, we have a bunch of graphs, a bunch of vectors as the graph of this function in the space. We call it a vector field, a field of vectors. X-axis, y-axis, and then z-axis. Well, you might have this behavior for your vectors. They might diverging. These are some vectors. This way, well, you can have different representation. They might have a linear relation. So it might be like this, depending on the definition of your vector field or vector function. It might behave like this. Go in the space. In the same direction. We're going to have different vector fields. Suppose example. Suppose I ask you to graph this vector field in the space. Example, graph this vector field. We have f of x, y, z equals to, well, it's given to us as z times k. Z times k, okay. What's the meaning of that? It means that the first component and the second component of this vector, both of them are equal to 0. You can write this vector function as f of highlighted f of x, y, and z equals to 0, 0, and z. What's the meaning of that? It means that if you consider any position for the particle in the space, the very first two, x and y, have no impact on the vectors. So let's graph this. This vector function. Remember that as we graph any function, we use point plotting. We take some points, we plug those into the function and start graphing. Use a table. You have some input values, inputs like x, y, and z, and also you have outputs. Outputs are just vectors 0, 0, and z. So it says the position, any position that you think about, like the very first position, suppose you are at the origin, 0, 0, 0. Well, the output value is going to be 0 vector. So the output value is 0, 0, and 0. Next, let's plug in, for example, 1, 1, 1. 1, 1, 1. This is the position. Input values showing the position of your particle. Then at that position, you have a direction. The direction is equal to, well, the first component is fixed, 0. The second component is fixed, 0. The third component is equal to 1. Okay. So 0, 0, 1. Suppose I choose a different position. Like, let's work with some negative numbers. -2, -3, and negative, for example, 4. So at this position in the space, what is the direction? Well, this is the function. The function is defined this way. The first component is fixed, 0. The second component is fixed, which is 0, but the third component is changing based on the third coordinate of your position of the particle that is moving. So the first component is 0, the second component is 0, and the last component is -4. So if you think about this vector field, if you want to try to graph this in x-axis, in y-axis, in z-axis, you have 0, 0, 0, which is your just 0 vector. 0, 0, 1. Okay, 0, 0, and 1. 0, 0, 1, 1, 1. So suppose this is 1, 1, and 1. So let's graph this together. First, we need the position, and here we're trying to graph this together, and let's see. So this is 1, 1, 1. 1, 1, 1. This is the position. 1, 1, and 1. What is the direction? The direction is 0, 0, 1. X is 0, Y is 0, but Z is 1 in the vertical direction. There we go. And the length of this vector is also 1. So we're going to use a vector with a length of 1. Next position. Next position is -2, -3, -4. -2, then -3, for example. Let's move this line here, and then -4. Everything is going to be down here. Okay. -2, and then -3. So it's going to be in this direction, almost here, hopefully. -2, -3, and -4. A little bit down with this respect. And then the direction is going to be 0, 0, -4. 4 units downward. 4 units downward. So we're going to have a longer vector, which is 0, 0, -4. Here you have your vector, which is 0, 0, and 1. So you can continue this process. You can plug in different values, find the position, and then find the direction at that position, and create your vector field. So this is the vector field that we have. The function is defined as 0, 0, and Z. And these are the vectors in 3D space. It looks like some of them are below XY plane. It's similar to the behavior of rain, but the ones that are going up, it's the opposite direction. This is our vector field. A field with a lot of vectors. These are all representation of a vector function. Very well, as usual, when you're dealing with functions, we are interested in some important characteristics of those functions. For any function, we're interested in finding the domain. Then we're interested in talking about the range of those functions. We're interested in analyzing the graph of that function. How do we take the limit? How do we define continuity? What about the derivative of that function? And finally, how do we calculate the integral? So for any function, these are the important characteristics. First, the domain. What's the domain of that function? Then you're interested in knowing the range of that function. How do we analyze the range of the function? Then, of course, we want to know what's the behavior. How do we visualize that function, the graph? After that, we're interested in knowing that, well, what's the limit? As we approach to a specific position, what would be the output value, the limit? Then, of course, talk about continuity. Well, and then limit and continuity, then we're interested in taking the derivative, the rate of change, the derivative of the function. And finally, how do we calculate the integral? So we define a new class of function. We define a new class of functions. What are those functions? Vector valued functions. Vector fields. Now we want to analyze vector fields, these functions, using the characteristics that we learned before. Very well. So suppose you have a vector field. Suppose f of x, y, and z is defined as, okay, we have p of x, y, and z, the very first component, then q of x, y, and z, and finally r of x, y, and z. This is a vector valued function or a vector field. To find the limit of this function at each point as x, y, and z approaches a, b, c, it's equivalent finding the limit of each of these components. Nothing too complicated, just taking the limit of each of these components. So this is equal to the limit of, so let me use a different color to differentiate between these. The limit of p, the limit of q, and the limit of r. The limit of p of x, y, and z as x, y, and z approaches a, b, c. Then we take the limit of the second component, limit of q of x, y, and z as x, y, and z approaches a, b, c. Then we find the limit of the last component, x, y, and z, and as x, y, and z approaches a, b, and c. That's how we find the limit of a vector function. What about the derivative of a vector function, a vector field? So this is the limit, then the derivative. To find the derivative of your vector field, you're going to take the derivative of each of these components. So for example, here you are writing down each of these x, y, and z in terms of a third variable like t. It means that, for example, you are specifically looking at your time and you're relating the position to the time. So now you can take the derivative with respect to, for example, time. Then you take each of these components with respect to time. So if we define a new variable like t, then we can connect x, y, and z, or the position of the particle to this new variable and find the rate of change. Very well. But when it comes to integral, we have more to offer. It's not just taking the limit or finding the derivative with respect to a third variable. When it comes to integral, we can define something that we call a line integral.